Hi friends, welcome to my YouTube channel. In this video, we will see how to reduce the variable layers of aspect, hillshade, slope, roughness and topographic position index, which is TPI in short, from the digital elevation model or DEM data. Here I have downloaded the Kato DEM tile from Google. And if you would like to download the DEM tiles for any region in India, please visit to one of my previous videos. And I have also uploaded a video explaining the steps to merge and clip the DEM to the region extent. Now, before reducing the layers, it is always suggested to fill the sinks in the DEM. Now, for this, type sinks in the processing toolbox. Sinks. Now, there are different methods to perform this filling the sinks option, and the commonly used and which I'll be showing in this video is the filling sinks by Wang and Liu. Now, here in the DEM, we need to select the digital elevation model. We are going to fill the sinks. For now, I am only interested in the filled DEM and I don't want the flow directions and the water basin. And flow directions and water basin, if you could reduce, this will be useful in finding the drainage layers and drainage maps. So for now, I'm going with filled DEM. And this takes a bit long time with respect to the area of the DEM tile and the region. So this is still processing. So here I have used only one of the DEM type. So this is algorithm is finished and complete. Okay, please. Now this is the field DEM. DEM means the digital elevation. That is elevation of negative 82 means below the sea level and the highest elevation with the land area. Now this is our field DEM. Now I'm going to save this as in yes, field DEM. So this is our field. Now I'll start with the definition of the variables we are going to deduce, and I say these layers to be variables as this contribute to the significant changes to some other environmental variables as well. Now the first one we are going to deduce is the aspect. Aspect denotes the slope's compass direction, that is the compass direction from 0 to 360 degrees, which is in the northeast southwest pattern. That is 0 degrees corresponds to the north, 90 degrees corresponds to the east, 180 degree corresponds to south, and 270 degrees for the west. Now to deduce that, we'll be using this raster option from the toolbar, under which you can see the analysis option and you can see the aspect as well. Now the input layer is the field DEM and we are going to do the aspect and let us save this also. Okay, I'm doing with tile E, that's why I'm naming as E. So run. Now this is the aspect layer. So we can see 0 to 360 degrees. Okay, so this is the aspect layer. Now the second one we are going to find out is the hillshade. Now, hillshade is a three-dimensional depiction of the sun's image on the surface. That is, this actually depicts the shadow and the light regions. So, this aids in the comprehension of the topological visualization of the terrain under the relative sunlight lightning. And these are related to the shades of gray, and the numbers ranges from 0 to 255. Now let us reduce the hillshade. We'll be using the same raster option analysis and under which you can see the hillshade. So the input layer is the field DEM and band 1 gray color. So set factors, these things are by default. Now let us save this hillshade. Now run. Okay, goes. So the hillshade actually ranges from 0 to 255 and our digital elevation model hillshade only ranges from 1 to 181. Now the third layer we are going to deduce is the roughness, which is actually the irregularity on the edge surface. And this calculation is based on the biggest intercell difference between a core pixel and its neighboring cells. Now let us deduce the roughness. Go to the raster option, analysis, and you can see the roughness. The input layer is the field DEM itself. So we are going to save this as roughness E. Can key the name according to your region to your wish. Now run. Okay, this is also complete. So roughness, aspect, hillshade, and roughness. Now the next one we are going to deduce is the slope, which is actually the rise or fall in the ground surface. So let us go to the raster option, analysis, and slope. Now for the slope also, the input layer is the field DEM. Let us save this into slope E. So this is our slope. Then the next layer is the topographic position index, which actually compares the height of each data point to that of its neighbors. And this aids in determining the terrain categorization by utilizing the topographic slope locations. So the subtraction of average neighborhood from the core cell height will lead to the computations of the TPI. So let us reduce the TPI raster analysis option and here topographic position index. So the input layer is the field DEM itself. Then let us save this into TPI E. Run. So this is the TPI. Now for a better visualization, we can change the properties of this layer also. We can go with the pseudo color. Then for roughness, let us take some shades of red. Okay. So quantile, classify, apply. Okay. Still, we can go with some other quantile instead of quantile equal interval maybe. Apply and let us see. Quantile. Okay, let us increase the class size. 8 and let, yeah, better. Okay. Increase the class size. Okay. So you can see the TPI ranges from here. Then let us configure the properties of the slope as well. So let us go with turbo classify instead of quantile. Okay, the layer is yes. This is the beautiful map of the slope. Then let us configure the roughness. So roughness, can we make it, let us invert this instead of continuous quantile. Classify, see how beautiful our gem tile and the area is. Now hillshade, it is actually in shades of gray, which is better. Now for aspect, let us go with some other colors. Mm, greens, quantile, classify. So this is this is the actual digital elevation model or the DEM type, and this is the field DEM upon which this is the aspect layer. First we reduced. This is the hillshade layer. Now this is the roughness layer, slope, and TPI. So thank you for watching and happy research.